Good morning to everyone. Myself, Dr. Chinna, Dastagiri, Goud, Assistant Professor from EEE Department. So, this lecture is in the course Fundamentals of Electrical and Electronics Engineering, and today we are going to discuss about the principle of generator action. So, especially the dynamically induced EMF. So, before going to the principle of generator action, so this is under the concept of DC generators. We already seen that what is generator, which converts the mechanical energy into electrical energy. So, principle of generator action, the basic principle of this machines. So, the basic principle is electromagnetic conversion. So, the basic principle is in all the machines. So, the basic principle of machines is electromagnetic conversion. So, it's a electromagnetic conversion. So, we discussed about this one and we seen the construction of the DC generator also. Here we are going to see some basic clocks on which the generators will work. So, generator means, as we said, it will convert mechanical energy into electrical energy. So, electrical energy means we see the EMF. So, these machines will induce the EMF. So, EMF means electromotive force. So, how this EMF will induce? So, it will be depend upon the two laws. So, which laws are derived from the father of electricity, Faraday. So, he explained the two laws. So, first one is Faraday's first law. So, according to the Faraday's first law, he said that whenever a conductor cuts the flux, it will induce the EMF. Like if there is a magnetic flux is there, if conductor is cutting the flux, that means the flux changes in the conductor, then it will induce the EMF. So, Faraday's first law generally it is explaining to us is how EMF will induce. It is explaining how EMF will induce. So, coming to the statement of this law, it is saying that when a conductor cuts the flux, an EMF will induce in it. So, here we will see the conductor is in action. So, conductor is cutting the flux, then it is inducing the EMF. That's why we will say the EMF induced in this process is dynamically induced EMF. So, this process, whatever is generator, if conductor is cutting the flux, then EMF is inducing, then it is known as dynamically induced EMF. So, conductor cuts the flux, then it is a dynamically induced EMF. If flux is changes in a conductor, then also it will induce the EMF. If flux changes in conductor, an EMF will induce in it. So, flux is changing here. Here if you observe, flux is changing here. So, then this is known as statically induced EMF. Conductor is at static position, flux is changes in that conductor. This is statically induced. So, here we are talking about the DC generator. So, when DC generator armature is rotating, that means conductors are rotating and flux is at constant position. So, conductor is cutting the flux. So, the generated EMF is induced EMF, dynamically induced EMF. So, and then what is the Faraday's second law is saying? This is the interesting part in the generator. We have to know how much EMF is generated. We know that EMF is generated, but how much? So, that is given by the Faraday's second law. Faraday's second law. So Faraday's second law is saying that the induced EMF is equal to rate of change of flux. The induced EMF is equal to how much EMF induced is explaining by the Faraday's second law. How much EMF induced. So how much is induced according to Faraday's second law is, that is the induced EMF is directly proportional to rate of change of flux. So he is saying that the induced EMF E is the induced EMF. So suppose we will consider induced EMF is E is directly proportional to d phi by dt. So rate of change of flux. So if generally if we take a proportionality constant, so that is E is equal to d phi by dt. So we will keep, sometimes if n number of turns are there, n conductors are there, we will keep n into d phi by dt. But here simply I am giving E is equal to d phi by dt. So this is the Faraday's first law and Faraday's second law they are saying. So there is a sub law, Lenz's law, so which is explaining that the induced EMF is always oppose the cause behind it. So then it will come E is equal to minus d phi by dt. Here I am not going in depth of that. We are going to check the principle of generator action. So we understand that this DC generator, while we are explaining, we have to know the dynamically induced EMF. So that is the point. So this is the dynamically induced EMF. We have to know about this dynamically induced EMF. That is the principle of DC generator action. So now we are going to discuss about that dynamically induced EMF. We are going to discuss about dynamically induced EMF. So what is dynamically induced EMF? As we discussed previously, when a conductor cuts the flux, it will induce the EMF. Whenever conductor cuts the flux, it will induce the EMF. So I am considering a two-pole machine to understand this one. So we will consider that a pole, two poles are available, that is north pole and south pole. We will consider that there is two poles. So this is a north pole and south pole. And we have a south pole. As we all know that flux will flow from the north pole to south pole. So this is the flux direction, north pole to south pole. So this is the flux, it is flowing. Now suppose we will consider a conductor. So now we consider a conductor. So which is, suppose we will consider, we have a conductor here. So we will consider that we have a conductor here. So this is the conductor. If this conductor is moving, so here we have to observe that what Faraday's law is saying, he said that whenever conductor cuts the flux, it will induce the EMF. So here if you see, if this is the conductor, suppose it is moving in this direction. From north to south. So definitely it won't cut the flux. It will be in the flux lines. It is parallel with the flux lines. So it won't cut the flux. So anyhow it won't induce the EMF. So when it will induce the EMF, when it is able to cut the flux, then only it will induce EMF. Suppose it is going exactly with 90 degrees. So exactly with 90 degrees, it will completely cut the flux, then it will induce the EMF to us. So here we are considering this one. So what is dynamically induced EMF? So we will consider a system, we will write it down. Let us consider a two-pole structure. Okay, so we have a two-pole structure with the flux density, B and phi is the flux per pole. Phi is the flux per pole or flux of the dust structure. So now we have the B and we have the flux per pole. Now similarly we have to consider a conductor. So consider a conductor with length L under this magnetic structure and moving a distance x in the field density in magnetic field density okay. So we are considering a conductor. So conductor length is L. So what we are saying, we have a two-pole structure with the flux density B and phi is the flux per pole, and we have a conductor with the length L. We have a conductor with the length L and it is moving a distance x. So here this conductor is there. Conductor is moving a distance x. We will consider that conductor is moving a distance x. Suppose it is moving x distance. It is moving x distance. So what will happen? So from Faraday's first law, so anyhow it is moving in this direction. So it is moving in the cutting the flux. So then automatically it will induce the EMF. So from Faraday's first law it will induce the EMF. From Faraday's first law, conductor will induce the EMF. Conductor will induce EMF. Induce EMF will induce EMF. Okay, so if it is inducing EMF, and from Faraday's second law, the induced EMF E is equal to d phi by dt. So now what we are doing, we have to find out this induced EMF. So what we have, so E is equal to d phi by dt, and what is d phi? The change in flux. So the change in flux, so it is a phi is the flux, so it will change flux is changing. So phi we can write that. So this d phi. So phi anyhow how much it is changing we don't know. So from we will come to the formula, we know that flux density B is equal to, flux per unit area. So I can write flux is equal to flux density into area. So I can write that. So we have option. So what I will do, I will introduce this one here. So what we will get, instead of d phi we will write d into ba. Here we know that B is the flux density, which is the constant for the structure. So B will come outside, so it will become, so B into dA by dt. So here what will happen, we have to know what is this area. So area, what is this area? So we want to know how much this is the length of the conductor L. So L is the length of the conductor, it is moved x distance. So we will get that area A is equal to length of the conductor L into distance covered by it is x. Now I will substitute that one, then we will get, if I will substitute that one, we will get B into dLx by dt. So where we know that length of the conductor is not going to change once we will take the conductor. So L also will come outside. So it implies E is equal to B L and dx by dt. So where you will see the dx by dt, so which is the distance traveled in the time. So distance by time we will take the velocity of the conductor. So the conductor how much speed it is moving. So then it will become, so BLV. So this is the EMF induced when this conductor is moving horizontal. That means it is cutting the flux in a distance. But sometimes there is no choice. It has to, see, this is the flux density B. So flux density B. So conductor exactly 90 degrees towards it. 90 degrees towards it. So whenever it is going 90 degrees, it is generating the EMF. So whenever it is at 0 degrees, it is not generating the EMF. So now we have to consider, suppose conductor is not going exactly in the 90 degrees. Suppose it is with some angle theta. Suppose, but if conductor is moving with an angle theta with flux density. I mean an angle theta with flux. So an angle theta with the flux lines. An angle theta with the flux lines. What will happen? So we know that now little bit mathematics we will see. Suppose this is the direction of flux density. Either you take the flux, so that is B. That is the direction of B. And this is the, so here simply I will give what previously we done. So previously we seen that this is the B. So this is the B flux density and this is the direction of X. So this angle is 90 degrees. This angle is 90 degrees. We seen it. But now it is not exactly going with some angle. Now we will see that suppose this is B is constant. So this is downside. This is B. And this is not the angle. So it is going with some angle theta. It is going with some angle theta. So I am taking this is the angle. This is the angle. So this is the theta. This is the theta. It is moving the distance X. It is moving the distance X. Then what will happen? So we can, what we will do? We can coordinate this X. This X we can divide into the two components. What is the X sin theta and X cos theta? So this already seen. So this is the X. So this part will become the X sin theta. This part will become the X sin theta. And this part will become the X cos theta. This part will become the X cos theta. So we all know that whenever this is differentiated between the x-axis and y-axis, we all know that this X cos theta is not causing any inducing EMF. Only this X sin theta is the reason for the inducing the EMF. So this X sin theta only we have to substitute. So here instead of dl into X, it will become dl into X sin theta, and sin theta is not depending upon the time because it is moving only in this direction. So theta is constant, it will come outside. So when conductor is moving with time theta, the equation is changed to E is equal to, it will become BLV sin theta. It will become E is equal to BLV sin theta. Clear? So clearly we are saying we taken the one structure, so which has the north pole and south pole, which has the flux density B and the flux is phi. So when a conductor is moving, so when it is moving exactly with 90 degrees, it is inducing the EMF. In 0 degrees, it is not inducing the EMF. So what we will do, we will move the conductor to distance X in time dt. So now we have to calculate if conductor is cutting the flux, then it will generate the EMF. So when it is generating the EMF, so the induced EMF value is from Faraday's second law, it is called E is equal to d phi by dt. So d phi by dt we taken, and what is the flux value? So here we will observe this is the, so from Faraday's second law, E is equal to d phi by dt, and the phi d phi by dt, phi is equal to magnetic field density into area, where from this formula we are getting flux density is equal to flux by area, and flux is equal to flux density into area. So we got B into A. So where we know that B is a constant from time because it is a flux density. So we taken B outside, that is dA by dt. And similarly, the area we have to calculate how much this conductor cover the area. So the length of the conductor is L and it covered the area distance X. So the area is L into X. So same thing I substituted here. And we know that the conductor L is the physical parameter of the conductor. So L came to outside. So BL into dx by dt, where dx by dt is the distance by time. So which is known as velocity. So V is the velocity here. We have to mention that. So we have to mention where V is the velocity. So we have to bracket V is equal to velocity, which is equal to dx by dt. Velocity of the conductor, which is equal to dx by dt. So we substituted that one. So then we got the E is equal to BL. But if the conductor is not moving exactly 90 degrees, it is moving with an angle theta, we have to consider the effective part in the EMF, induced EMF equation, that is the x sin theta value. So if we substitute that, we'll get E is equal to BLV sin theta. So this is the dynamically induced EMF and the principle of generator action. Here we'll get doubt that, so we know that what is the magnitude by the conductor when it is moving in a magnetic field. So the induced EMF is BLV sin theta, and how we can find out the direction of current. Direction of current. So for that one, we'll go with the Fleming's right hand rule. We'll go with the Fleming's right hand rule. So this is Fleming's right hand rule. What Fleming's right hand rule is saying? Fleming said that the basic principle what we discussed, electromagnetic conversion. That means there will be electrical conductor will be there in a magnetic field when it will rotate. Rotate means conversion. Conversion is done by because of that action, converting action. So these three things he taken into 3 fingers. So what he told, we have to take right hand rule. So for generator action, we will use the right hand rule. So in right hand, he taken the 3 fingers, that is thumb, forefinger and the middle finger. So electromagnetic conversion. So middle finger will represent the electrical terms, there is the current. What is the direction of current it will show. And the forefinger will show the magnetic. So it will show the direction of the flux. And thumb finger will show the motion, which direction conductor is moving. So in a magnetic field, when a conductor is moving, what is the direction of current? This is the 3 fingers will represent. So we'll say that what is the statement? Fleming's right hand rule. Fleming's right hand rule. When the thumb, forefinger and middle finger of a right hand kept perpendicular to each other, So how we can keep perpendicular to each other? So if you see, this thumb finger is exactly 90 degrees with the forefinger or index finger, and at the same time, if you see, this is the angle, this is the middle finger, this is also 90 degrees, and similarly this forefinger is 90 degrees with thumb and 90 degrees with the middle finger also 90 degrees with the forefinger and the thumb finger. So if you want to understand, you can take the one corner of the house. So upside, that is the thumb. So on right side, one side you take the middle finger, one side you say the forefinger. So that will represent, if you see, this is your corner point of the house, this is the thumb finger. So this will represent your one side, this will represent another side if you keep it. So this is exactly each other 90 degrees. So if you keep each other, he said that the thumb finger, so here we will see, so I am writing as a point, so the thumb finger, so thumb finger has to be in the direction of conductor. Thumb finger will be in the direction of motion of conductor. So which side it is moving. And next one is forefinger. forefinger. Shows the direction of field flux. Field flux. And what left? The middle finger. The middle finger. So if you keep these two in the direction of the motion of the conductor and direction of the field flux, the middle finger will shows the direction of current. The middle finger will shows the direction of current. Direction of current. Direction of current. So that is Fleming's right hand rule. So here I represented with the double letter. M means motion. So it is the field flux. Then I is the middle finger. So we can remember that thumb finger will show the motion of the conductor. Forefinger will show the field flux direction. And then we will get the current direction from the middle finger. So that's why you take in the right hand. If you come from the thumb, so motion of the conductor, field flux, if you give direction, then it will give the direction of the current. So for example, suppose we have this is one north pole. So I am taking again one this is a north pole and this will be the south pole. So as we all know, flux will flow from the north to south. Flux will flow from the north to south. Okay, so this is the direction of the flux from north to south. North to south. Now I will take the conductor. Now I will take one conductor. So this is my conductor. So this is my conductor. So conductor is moving. So suppose this is north pole and south pole. So conductor is rotating in the clockwise direction. We will consider conductor is rotating in the clockwise direction. It is rotating in the clockwise direction. So when what is the direction of current exactly at north pole? What is the direction when it is at exactly north pole? What is the direction of current? So here we will see what is the flux direction. We will take our forefinger from north to south we kept. Then conductor is moving upside. So my finger will be upside. So if you see my middle finger, it will be towards the PPT. That means inside the PPT. So the conductor current is going inside. So as we mentioned, this is a conductor. For inside we will mention with the cross into the conductor, and it is coming out of the conductor. We will draw with the dot. That is the out of the conductor. Okay. So this is the representation already we discussed. So now it is going into the conductor. That means suppose if you see the into the PPT it is going. That's why I kept the into mark. So now it is moving exactly. It came to the suppose south. The conductor came to south pole. Now tell me what is the direction. If you see flux direction won't change. Definitely it will be from north to south. But conductor is moving in clockwise means conductor is moving downwards. Conductor is moving downwards. So that means thumb is downwards and flux is upwards. If you see the middle finger is out of the PPT. Middle finger is out of the PPT. So that means current is coming outside the conductor. It is not going into the conductor. It is coming out from the conductor. So we will represent with the dot. We will represent with the dot. So I hope you understand how we will, what is the direction of conductor we will find out from the Fleming's right hand rule. Suppose here you take as a task, suppose at north pole, I want current has to go into the conductor. What we can do? So we can do that. Simply it is instead of rotating in the clockwise, if you say that it is rotating in anti-clockwise, then current direction will become out to the conductor. And same thing at south pole, suppose it is rotating in the anti-clockwise direction, current direction will become into the conductor. So please check this one so that you can understand the operation of the DC generator easily. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.